Okay, this is the 5.1 through 5.4 review covering the trig identities. I want to talk a little bit about the PowerPoint slide that I showed the other day. Just to had all these in one kind of nice organized list, and just make sure we're clear on where to get everything and what we're doing. So again, it looks like a lot to memorize, and it kind of is, but really there's a lot of background stuff that if you just remember a couple of things, you really can come up with a lot of the rest of it. So looking at the chart here, this page here, I think the top left, those reciprocal ones are ones most people were familiar with. We've been using those quite a while. And right below there, the tangent being sine over cosine, we've done that quite a bit. Um, in the middle, the squared, all the squareds are your Pythagorean identities. So it kind of all started with the one on top there, cosine squared plus sine squared equals 1. And we actually proved that by drawing a triangle and then kind of showing how that the cosine squared, so it would be adjacent over hypotenuse squared plus sine squared, which would be opposite squared over hypotenuse squared, would equal 1 because the numerators are opposite squared plus adjacent squared, which by the Pythagorean theorem in any right triangle is the hypotenuse squared. So we went through that. And then below those are the other variations there where if you were to take the original one and if you divided both sides or every term by cosine squared, you would get the 1 plus tan squared equals secant squared. And then also if you took the original top Pythagorean one and divided all three terms by sine squared, you would get the bottom one there. Cotangent squared plus 1 equals cosecant squared. And just remember, you can do subtraction and move things around and get up to 9 actual total variations of those. And those show up quite a bit in these problems, as you can see. Top right there, those are your even odd ones. Those really don't show up that much, but they're just kind of good to know at times. And they can actually be derived from the sum and difference ones, the ones on the bottom right there. You can think of, if you're looking at the sine of negative x, that's really just like sine of 0 minus x. Okay, because that's 0 minus x is negative x. And if you apply the sine sum and difference formula, you would end up with negative cosine x, or I'm sorry, negative sine x. And other than that, I mean, the bottom left, those are directly coming from the ones right next to them with the sine a plus b. We did those in class, so just make sure you're aware. If anything to memorize, I would say the sum and difference ones, so the bottom right box there, and the Pythagorean ones can really get you everything you're going to really need here. Okay, so let's go through a few examples of solving some problems. These were actually taken from, I think, a quiz that we did. So let's go through a couple identities. Um, so this is version A of the quiz if you have that in front of you. So sine x times cotangent x plus cosine x tangent x. And we want to prove that that equals cosine x plus sine squared x. Okay, so myself personally looking at this one, I'm looking at the left side being a little more complicated. So what I would encourage you guys to do, divide it up. Like, don't work on both sides, really. You can't do something to both sides. You can work with one side at a time, though, okay, and do little things until they match. So what I'm thinking is this sine x here, and I'm going to get everything in terms of sines and cosines. Like, I see a cotangent there, so I know that that's just cosine x over sine x. Okay, this cosine x over 1 just to make it a fraction, and then it's getting multiplied by tangent of x, which is sine x over cosine x. Okay, and then here's where there's some issues, because in this problem now there's fractions. Okay, looking just inside this big term right here, there's fractions being added, but there's also a multiplication step. So it's always an issue of what can you cancel, when can you cancel. So with these two in particular, they're getting multiplied together. So if I see a common factor of a cosine and then the cosine being divided out, those two actually can cancel each other out. Okay, not the other one with the cosine over sine just to the left there, but since these are being multiplied, we can do that. So what we really have is sine x. This is cosine x over sine x still. And this other term is really just sine x now. Okay, because again, the cosine's canceled there and there. So Now, okay, so it's kind of unclear. Do we want to get a common denominator in the parentheses because there's fractions? And that's something you could definitely do, but here's where I would suggest take a peek to the other side and see what you're trying to end up with. And it kind of looks like if we were to just distribute this sine x right here, that we would get exactly what we have over here. So there's no right or wrong way, but this is just going to make it a little easier. And if you're peeking, look at what your goal is. You don't always have to do a common denominator. Okay, but hopefully you can see again with the algebra just distributing there that we do get what we wanted. Okay, and one last thing on this problem too, and on any of these actually, make sure you guys are showing like clearly one step to the next and go and right below the step. I wouldn't want to write to the right, like I wouldn't want to, if I'm at this point, I wouldn't want to continue and do the algebra over here. I'm thinking of this, I'm working on only the left side of the equation, so technically what I'm doing is working straight down the page on the left side and just show every single step, okay, even the basic substitutions. That's the whole point of these problems. It's kind of like the answer, like they're telling you what it needs to look like in the end. The actual work and the importance of the proof is in the steps here. Okay, so that was the first one. The next problem on that version was something like cosine of b over 1 plus sine b. And we want to show that that equals 1 minus sine b over cosine b. Okay, and this one there's definitely options and different ways you can do things. I see in the left term on the bottom, it's a binomial there, so I could actually multiply by its conjugate, and that's usually a good thing to try. Okay, so let's do that as long as we do top and bottom by the same thing. Okay, I'm really just multiplying that left term by 1, right? 1 minus sine b over itself. So if we carefully distribute that out, up top, just distributing out, we're going to get 1, I'm sorry, we're going to get 1 cosine b minus sine b cosine b. Okay, and on the bottom, here's where this is going to help us, and make sure you see this. What happens when you multiply conjugates is the first term gets multiplied, then it would be a plus sine b, but then it would be a minus sine b. So those will always cancel out, and the last term will always be whatever the second one is squared. Okay, so 1 minus sine squared b. And the reason that that's so helpful, and the good thing that conjugates do for us a lot, is you usually, or sometimes you get a Pythagorean identity. Okay, this right here, let's just work off to the side here. If you remember sine squared plus cosine squared is 1, that's the main Pythagorean one to remember. Hopefully you're recognizing if you just subtracted sine squared from both sides, you would end up with cosine squared equals 1 minus sine squared. Okay, and I should be writing the b or the x after those, but that's exactly what we have. We have 1 minus sine squared in our denominator, so I can replace it with cosine squared. Okay, so here's my numerator that we haven't touched in this step. The denominator is getting replaced by cosine squared b. Okay, and now's the time where I might want to look up at my other side here and see what our goal is. I want it to look like this, and it looks fairly close. Okay, but what we can do is notice the denominator needs to be cosine b. Right now in blue there we have it as cosine squared b, but I'm also noticing there's a cosine b in each of these. Okay, so just to make sure we do our reducing and canceling correctly, what actually happens here is we factor out this cosine b from both terms. Okay, so it's kind of like undistributing, right? You factor it out. Cosine b, we would need to multiply that by 1 minus sine b. Okay, it's just like distributing backwards, right? I know that kind of confused some people because we haven't factored a lot with trig functions, but really that's just a common factor of cosine b. Okay, so make sure we see that. So this term and this term was in common, so I just brought it out front. Okay, and then ask yourself if you were to distribute that back, that's why this is a 1 and that's why that's a sine b. Okay, and now we are able to cancel, reduce, actually divide out. There's a cosine in the numerator, it's a factor. There's a cosine squared in the denominator. So that will actually cancel out the squared part and we will be left with exactly what the other side of the equation was. Okay. Okay, I'll do the angle exact value one in just a second. It was on the back from section 5.4 or 5.3. But let me do the other proofs real quick. The other version had 1 minus cosine of u times 1 plus cosine of u all over cosine squared u. And we want to prove that it equals tangent squared u. Okay, and again, let's think we have two sides of the problem. I don't want to work with both. Clearly in this one, the left side is a little messier. Okay, but again, think about, if you think tangent squared, you should be thinking, if you want to do this step, you could think that's tangent squared sine squared over cosine squared. Right, that's one kind of way to think about this. And looking at your other side, it already has the cosine squared in the bottom. So if there's a way to get that numerator to be sine squared, we would be set. So if we multiply that out, they're conjugates, right? So it's going to be 1 minus cosine squared u, and the denominator is cosine squared u. Okay, and it's tempting to cancel those cosine squareds, but we can't because the numerator is not a multiplication problem. Okay, so again, think about dividing by cosine squared isn't going to cancel out that subtraction in the numerator. But we do know from our Pythagorean identities, like a previous problem, 1 minus cosine squared, if you check your Pythagorean, is going to be equivalent to sine squared. And that works perfectly, because look at our other side was sine squared over cosine squared. Okay, so you can kind of do a little on both sides, or if you wanted to, on the left side, put tan squared beneath that, and you wouldn't have had to do this step over here. Okay, both sides are equal, we're good to go. Okay, and the last identity was tan squared x over secant x plus 1. And the other side is 1 minus cosine of b over cosine of b. Okay, and this one again, like one of the other, most of these problems have multiple options. For whatever reason, I always tend to start on the left side. So if you wanted to do conjugates, you could do that, multiply by secant x minus 1, or you could use a Pythagorean identity to replace the tangent squared up there. Or similarly, another option that would probably work would be to times this right side by 1 plus cosine b, top and bottom. Okay, so they're all out there. The one I went with again was the conjugate one, just because for whatever reason it seems to usually work. So again, conjugate is just going to change the plus sign to a minus in there. We're going to do the numerator and denominator by the same thing. So what we end up with if we distribute, so secant x times tangent squared, okay, and then distribute the 1, so just minus tangent squared. Okay, the denominator now, conjugates, right? So it's the first one squared minus the second one squared. Okay, and now I'm actually noticing the numerator can be factored. And actually, if we would have just left it the way it was before, as tangent squared, okay, so again, a common factor, kind of like we saw in one of the other problems, bring out the tangent squareds, and you'll be left with secant x minus 1. And actually now looking at the denominator, again, before we even multiplied it out, okay, since I see this secant x minus 1, and this one actually had it too, so I would probably be better off not have multiplying that out. So let me just put it back unmultiplied, where it was just secant x minus 1 times secant x plus 1. Okay, because that will allow us to cancel, or to divide out a common factor. Okay, top and bottom both have a secant x minus 1. Okay, and we could have actually done that, I guess, from the very first step. See up here, let's see what we end up with here. So that one cancel out. All right, it looks like I'm going in circles in this one, aren't I? Secant x plus 1 Okay, so again, I'm kind of going in circles in this one. Let's maybe try another method. Because what I have left now is exactly what we started with, isn't it? Tangent squared x. So sometimes that happens. So let's try something else. Why don't we do a Pythagorean identity? Okay, why don't we replace the tangent squared with something? This might work out a little bit better. Okay, and this happens sometimes in these problems, even if I've been doing these forever. So don't feel discouraged if that happens. Um, but tangent squared, if you look at the other Pythagorean identities, is equivalent to secant squared x minus 1, right? Okay, there's our original denominator, right? Okay, now what ends up happening is that is actually factorable. Okay, that it's the numerator is really just secant x minus 1 times secant of x plus 1. Okay, it was the difference of perfect squares, right? And that actually allows us to cancel a common factor of secant x plus 1. All right, and here's why this is going to work now. Remember, the other side of our equation, just to keep it up here, was 1 minus cosine b over cosine b. Okay, so what you can actually do if you wanted to, I'm working on the right side now, whenever you have a fraction and the top part is like more than one term added or subtraction, you can split it up. It can become 1 over cosine b minus cosine b over cosine b. Right, it's just kind of like undoing when we combine them to be one big fraction. And hopefully we're recognizing that in red right next to that there is exactly what we have, because 1 over cosine is secant. And sorry, this was supposed to be all the variables were supposed to be x. I think I had a little typo on there. So this 1 over cosine is secant x, and then cosine over cosine is 1. Okay, so that one, sorry, we went a little bit in circles, but again, that's just kind of what happens with some of these. And that's just one option. There's different ways to do it. Okay, now let's do one of the exact values just to get through the double or the angle sum and difference formula. One of the versions asked you for the cosine of 105 degrees. Okay, so the issue was we don't know that. It's not on our unit circle. So we don't have an exact value, and we need to be exact here. I don't want a decimal. You can use a decimal approximate to check. But the idea was take the angle, split it up into angles that you know from the unit circle, like 30s, 45s, 60s, okay, or in any of the given quadrants, any of those reference angles. And 60 plus 45 is going to work. So we have like an A and a B here. And then we had a formula that said for the cosine of a sum, it's cosine of the first, cosine of the second, minus sine of the first, sine of the second. Okay, so that was one of those double angle formulas in the bottom and the middle box that you just kind of need to know. And now each piece of these is something we should know. Okay, the cosine of 60 degrees. Okay, that's half from our unit circle. Cosine of 45 is root 2 over 2 from our unit circle. Sine of 60 is root 3 over 2. And sine of 45 is root 2 over 2. Okay, so we broke it into angles that we know. If you didn't use angles that you know, then you're not going to be able to do the problem any better than when you started. Okay, so now if we just kind of simplify, multiplying these two together, we multiply straight across. The top is just square root of 2. The bottom is 2 times 2 is 4. And the other piece multiply again straight across to get square root of 6 over 4. Okay, and sometimes we like to just write it as one big fraction. And that is it. That's your angle sum and difference formula in action. All right.